No product is absolutely reliable. Products regularly fail or malfunction in the course of ordinary use. Some product failures are foreseeable and easily preventable. Many other failures, however, are unexpected and often result in significant monetary and property damages and even lead to loss of life. Prevention of potential failures in new and existing products is imperative to an organization's survival and competitive advantage. Unfortunately, manufacturers regularly incur huge costs related to product recalls, warranty relief, and litigation ensuing from poorly envisioned and executed products and systems. Failure Mode and Effects Analysis, FMEA, is the primary approach used across industries in identifying possible product failures. When conducting FMEAs, engineers ask, what can potentially go wrong here? Finding the answer to this question usually involves numerous and tedious brainstorming sessions. The randomness of brainstorming cannot guarantee that all potential failures are discovered, and that no major ones are missed. In a complex system, such as an automobile, thousands of failure modes may occur, and a comprehensive FMEA may take weeks to complete, even by a team of experienced specialists. The subjective outcome depends heavily on the personal qualifications of these specialists. Complexity is further exacerbated by the integrative nature of modern products, which incorporate highly diverse components based on mechanical, electronic, thermal, chemical, and other properties. Such diversity makes it extraordinarily difficult for engineers, most of whom are narrow subject matter experts, to effectively communicate with one another during the FMEA stages in the product development process. As a result, a comprehensive analysis of a relatively simple assembly, one consisting of just 15 to 20 parts, may take weeks to complete. Yet the experience of thousands of manufacturers around the world clearly demonstrates that even such lengthy analyses may still result in incomplete FMEAs, and all too often in major systemic failures. Naniva has developed a breakthrough software solution for the automated detection of potential failure modes in products and processes. TechScan enables the recognition of potential failures caused by numerous and diverse factors, such as mechanical fatigue, thermal and electrical stresses, erosion and corrosion, variations in production, typical wear and tear, and many others. TechScan is a universal solution. It is adaptable to the task of automating failure diagnosis in virtually any product, from a child's toy to an aircraft carrier. TechScan is based on the original method for modeling cause-effect chains in complex technological systems. TechScan's knowledge base contains models of hundreds of typical components. These are bolts, nuts, springs, shafts, bearings, seals, valves, motors, wires, switches, and countless other components. The model of a typical component takes into account the streams of energy and materials that flow through this component, as well as the materials the component is made of. These component models, similar to Lego pieces, allow for the construction of the prevailing majority of modern products and technologies. To understand how TechScan works, consider a somewhat simplified analysis of a generic automotive side view mirror. The side view mirror is a multi-component system comprised of mechanical, electromechanical, optical, and electronic parts and assemblies. TechScan analysis of the mirror begins with building its structural model. Next, a functional model is built. Various other components and factors are taken into account: adjacent parts, numerous environmental factors such as wind, moisture, vibration, heat and cold, the driver's hands, etc. The functional model is ready. We can now run the failure mode simulation. Suppose we want to find out under what conditions the mirror lens will not move. We assign the failure mode absent to the function mirror turn and click the simulation icon. Several seconds later, the screen changes. It now shows numerous cause-effect chains that may lead to this major failure. A detailed description of all the detected failure causes, and there are dozens of them, is found in a report generated upon the user's request. TechScan is capable of analyzing really complex systems comprised of dozens and even hundreds of parts. To this end, multi-component systems are represented as single assemblies. This approach allows for finding out how a change in one part of a complex system might affect other remote parts. The model you're observing on the screen includes the side view mirror, the ignition system, the fuel pump, and the engine. What might happen when you insert the key into the ignition switch, turn the switch on and decide to adjust the position of the mirror. The pivot motion of the mirror will cause the DC motor to rotate, thus converting it into a DC generator. The voltage from this generator will flow, via the external circuitry, to the ignition system, and from there to both the fuel pump and the engine. This may result in a spontaneous start of the engine. An unlikely scenario? Well, several years ago, this exact failure mode forced one automaker to spend millions on warranty relief. Notice the speed and comprehensiveness of the TechScan-based analysis. Now then, let us sum up. TechScan's benefits are extraordinarily high speed of analysis, unattainable via conventional or manual FMEA. High reliability of failure detection. Universality. The ability to rapidly analyze complex systems. Applicability to the early stages of the product development process. Unlimited model reuse and editing.